Good morning. Today we're going to be solving the peer review problem 6, Euler's method. So let's recall from the notes that the Euler method involves obtaining the approximation to the solution at time step k plus 1, which is equal to the previous time step of k, plus the forcing function of y of k, t of k, which is multiplied by delta t. So here we're going to show graphically what exactly this means. But first of all, let's remember we're solving a first order ODE of y of dash, which is equal to the forcing function of y t. We're also given some initial conditions at y of t of 0 equals some number y of 0. So let's see what happens at the time slope k equals 0. Now how do we get y t of 1? We get this from subbing in k of 0 into the previous equation, which gives us y of 0 plus forcing function of y of 0, t of 0, which is of course equal to 0, multiplied by delta t. Okay, so let's see what this means graphically. So let's make a plot of the numerical solution y versus time t. So we start at this point of time 0 with a given value y t of 0. And now we want to find what our approximation at t is equal to, which we'll label delta t. Remember, delta t is this distance here. So somewhere along this dotted line is going to be y t of 1. But how do we get that from y t of 0? Well, you can see here that f tells us the time derivative of the solution. So if I take the time derivative and multiply it by delta t, then I move delta t in the direction of that slope. So f, or y dash, is the gradient of the time derivative at this point. So let's suppose, for example, that this line here has a slope of f y of 0, 0. Okay? So this slope tells us the time derivative of the solution at this point. Now for the Euler method, we just follow this line until a distance of delta t, and once we hit this point, forward in time, we have arrived at our new numerical point y t of 1. So if we follow this line here until delta t, we now have our new point y t of 1. This process will continue. For example, if I wanted to do another delta t that brings me to 2 delta t, with this distance being delta t, I need to evaluate the slope at time step 1. So let's suppose now the slope looks like so. So the slope here is f of t of 1, y of 1. And now I'll follow this slope until the next point, 2 delta t, which arrives at this point, which will give us our new point y t of 2. And this process will continue on for as long as you like.
So then, we are now tasked with using Euler's method to approximate y of 1 given the differential equation y dash equals minus 2 t squared y, and the initial condition y of 0 is 2 using the step size 0.1. I start by writing out the formula for Euler's method. Y subscript k plus 1 equals y subscript k, plus our differential equation for y with the in y multiplied by our step size. I start by finding the approximation for our first iteration by implementing this formula using the values for our initial condition. So y of 0.1 equals 2 plus the differential equation with our values 2 and 0 subbed in for t and y, multiplied by 0.1, which we can see here. This 0 ultimately equals 0, so we end up with a value of 2. Then we continue implementing this to find our y of 0.2. So it's the same process implemented 10 times until we get y of 1, which as you can see is a fairly lengthy process, so I won't talk you through it all, but as we can see, for y of 0.2 we get an approximation of 1.996, for 0.4 we get 1.944, for 0.5 we get 1.882, for 0.9 we get 1.305, and finally for y1 we get 1.094. So, the next thing we have to do is compare this value with our exact solution, which we can find by recognizing that our equation is separable. So carrying y over and integrating both sides, we get log y equals minus 2/3 t cubed plus c. We can write this out with e to the c value here as a, and by implementing our initial condition, we find that a is equal to 2, therefore the exact solution is y equals 2e to the minus 2/3 t cubed. Subbing in 1, we can then find a value which we can compare to our approximation of y1 we got using Euler's formula. So to compare these values, I've calculated the absolute error by finding the difference between these two values and absoluting it, and we get 0.0669, and I also found the relative error, which is found by finding the difference of these two values and dividing by exact solution and finding the absolute of that. So that is 0.0937, which is 9.37%. So both of these values you'll notice are relatively small. They could be a lot smaller, so clearly the approximation isn't absolutely accurate, but that's to be expected, hence why it's called an approximation.
As can be seen in the graph, the dark blue line represents Euler's method, of which the data values for 0.1 to 1 were plotted and then a line was drawn between them. The yellow line is a line generated by using the exact method of y is equal to e to the negative 2/3t cubed, and then the numerical values were calculated to find the difference between, as can be observed, the exact method and Euler's method, and then plotted underneath, and it becomes less accurate the further along we go.
Finally, how can we improve the approximation of all the methods? Examine this Excel sheets, which including exact solution and all the methods with a step size of 0.1 second, with the addition of approximation using all the method with a step size of 0.05 and 0.025, half and 1/4 of the initial step size respectively. The final data and the differences compared to exact value are clearly shown in the sheets. Exact value after 1 second is 1.0268. All the method with 0.1 second gap is 1.0937, with differences as 0.06686, and with 0.05 second is 1.0589, and the differences is 0.03206. And with 0.025 second gap is 1.0425, and the differences is 0.01571. Clearly, the differences with older method with 0.02 second gap is smaller than the 0.1 second and 0.5 second gaps. This graph has been drawn according to the spreadsheet, where it is even more clear that older method with shorter time gap has better accuracy than longer time gaps compared to the actual values of real line. This is because the older method is a first-order method that draws multiple tangent lines from the given starting point that line up together. The tangent line only has one intersection with the curve, therefore larger time gap in older method creates more distance on the tangent line before next line is created. It is major reason that the differences or error comes from. For this reason, older methods approximations accuracy can greatly increase by just simply decrease as many step sizes as possible.